Okay, so we've seen that the equivalence between the match filter receiver, which is a linear sampling receiver, and the results of the signal space analysis, which led to a correlator. And so now we're going to look at the next important outcome that we get from our signal space analysis. So the signal space analysis so far has given us a form of the receiver, and now we're going to use it to find how the performance of these receivers can be calculated, and that is known as the bit error rate. So we're going to be using signal space analysis in order to find the bit error rate for multidimensional signaling formats. However, before we go into that more difficult case, I want to just take the binary case, but look at it from the signal space analysis because it's a simple way of doing our first calculations of probability of error and getting comfortable manipulating the Gaussian distribution in order to calculate bit error rate. So we could have, for instance, done this same analysis of the bit error rate when we simply looked at the matched filter receiver. However, I decided to wait until we do the signal space analysis because I think that we can take a simple example binary case, gain a little bit more intuition, and then move on to doing the higher order modulations. So, binary case to begin with. And this is known as on-off keying or antipodal modulation and is covered in section 3.2 of the Sklar textbook. So we've said already that noise is the key for finding the bit error rate, that the noise density is what determines our calculation. And so we've already gone through in the signal space analysis coverage of what the statistics are for the noise coefficients in the signal space vector of noise. We found that they were zero mean, and the variance was given by n0 over 2. They have independent coefficients in the noise vector, so the expected value of the product of any two elements of that vector is 0. And the total joint density, the joint density function for the vector of noise is given by this product of the marginal densities due to the independence of the coefficients. And so this is the Gaussian distribution for each one of these coefficients. So the coefficients are independent and identically distributed. They're IID, which is this density. So we're going to look now at the binary case, and in fact we're going to look at two different modulation choices for the binary case. The first case is to use antipodal signaling, and the second case is to use what's called on-off keying. So antipodal signaling means that we basically have one waveform, and in this case the waveform we'll be examining is rectangular. So the logical one is a positive A voltage between the time of 0 and t, and 0 elsewhere, and the logical 0 is simply the negative of that waveform. So one of them is positive A amplitude, the other one is negative A amplitude, and this is antipodal by definition. In the second case, we're going to use the same waveform, so the logical 1 has exactly the same shape. It's just that for the logical 0, instead of sending the negative of the logical 1, what we're going to do is send nothing. It's going to be a signal of 0 for this transmission. So these are two different modulations that we could use. In both cases, they're binary. And we would like to compare the performance of these two. And how are we going to do that? So we're going to use signal space analysis in order to find is the performance better for one or the other, or is it comparable? What's the difference? So how do we do that? Well, we know that when we look at signal space analysis, the first thing we have to do is represent these signals in the signal space. And to do that, we can use the Gram-Schmidt process. So here we're going to apply the Gram-Schmidt process to antipodal signaling. And the first step of the Gram-Schmidt process is to take the first symbol vector and to simply normalize it and make it the first basis vector. So in order to normalize it, we go down here and we create the calculate the energy in this first symbol. And it's quite simple because it's a square wave, so it's just the integral from 0 to t of a constant, a squared, and that gives us a squared times t. So if I want to normalize this to make it unit energy, that means I will be dividing by the square root of this energy, and C1, the first basis vector, is just given by 1 over the square root of t from the interval from 0t to capital T. And it's 0 elsewhere. Excuse me. So now, if I were to keep doing the Gram-Schmidt process, of course, I would get that the second basis vector is 0. How do I know that? Well, let's go over here. I know that the S1 of t, S1 of t is equal to C1 of t with some normalization, so a the square root of t. So they're the same vector, different lengths. C is normalized to have unit length. Now I know that S0 of t is minus S1 of t in antipodal signaling. So I already know what the representation is for S0 of t in this basis. It's going to be just minus C1 of t times a square root of t. So here I have the coefficient for this vector is simple to see. It's an a square root of t. Okay, so clearly my Gram-Schmidt process has stopped because my S0 can be represented with this first basis vector. How did we know that? We could have also known that before we even started, because since S0 is equal to S minus S1, that means that S0 is a linear combination, in this case just multiply by minus 1, of another symbol. And whenever we have that, we reduce the dimensionality of the symbol space, signal space. So let's go on to the second case, which is on-off keying. And we'll go through the Gram-Schmidt process again. And, once again, we get the same result because it's the same S1. So we get the same basis vector. And of course, when we're talking about on-off keying, OOK, in this case, S0 is just equal to 0. So I certainly don't need another basis vector in order to represent the origin. So we have our Gram-Schmidt process, and they both came up with the exact same basis vector for either one of these two modulation formats. So if we want to write them as vectors, here we'll take the two symbols, S1 and S0, and we write here their coordinates. And in the S1, the first coordinate is a square root of t, and for S0, it's just the negative of that. So now we represent them as these two vectors, and of course the signal space we see is of dimension 1. There's one basis vector. So the space is just a line, very simple signal space. In the case of on-off keying, something very similar. We get S1 and S0, the same S1, but of course S0 is just 0 in this case. It's a single point at the origin. There's no energy because it's just the point at the origin. So this one-dimensional space, that means that in this one-dimensional space, when I receive a signal R of t, what I'm going to do is calculate, of course, the inner product of R of t with the basis vector, which means I'm going to correlate the received signal with the symbol shape. And in this case, there's only one shape. It's used for S1, and the negative is used for S0. So very simple. I take the received waveform R of t, and I calculate this correlation with the waveform. And again, we've already seen that the sampling receiver would have had us do a filter followed by a sampler, but that's exactly the same result as this correlator version. So now that I have found the coordinates in the signal space, I'm going to plot them, because the whole point of signal space is to give us more intuition. And so now I plot these two vectors in the one-dimensional signal space, and they're pointing in opposite directions, hence the name antipodal. And one of them has coordinate a square root of t, and the other one has coordinate minus a square root of t. And here they are traced in red and in blue. And we can observe that they of course have the same length. They have the same energy. These two are equal energy symbols. Now let's look at case 2 with on-off keying. And the first S1 symbol vector is the same as in the case of antipodal. However, the logical 0 has only 1 point for its vector representation. So clearly, these two symbols are not of equal energy because the logical 0 energy is 0. Now, if I'm going to compare these two modulation formats to be able to see if there's an advantage to one or the other, I have to make a fair comparison. And this is something that's going to come up very much in our analysis. And that normalization that I must do is going to be based on the average energy of a symbol. And since this is binary, a symbol is a bit, so I'm going to make it so that these two modulation formats that I examine, I'm going to normalize them so that they both have the same average energy per bit. Very fair, because if I have twice as much energy in one system, of course it would be normal that it might perform better. So if I want to see really how the noise is being attacked in the system, I really have to normalize to this average energy per bit. So that will be our next step. So I have to calculate what is the average energy per bit. And the first step is to calculate the average energy for each one of the bits. And of course, in this case, we knew that geometrically there was same length, so of course they'll have the same energy, a squared t. And if I find the average energy per bit, 1/2 of each, well, of course I get the same thing. So a squared over t is the average energy per bit in this antipodal. So if I'm going to normalize them, that means instead of talking about a squared t, I'm going to instead represent it in this new symbol, which is the EB, or the average energy per bit. So every time I see a square root of t, it's the same thing as saying, well, that's the square root of the energy, the average energy per bit. So I'm taking this space, and in the signal space, I am renormalizing it so that the length of the vector can be directly related to the energy, average energy per bit. So now let's what happens when I look at on-off keying. When I look at on-off keying, first of all, the first symbol has the same energy as in the case of antipodal signaling, but the second one has 0 energy. So now the average energy per bit ends up being different in the on-off keying case than in the antipodal case. And in fact, in the on-off keying, the average energy per bit is 1/2 of the example in antipodal. And I want them to be the same so that I compare them fairly. So what I'm going to do is I'm going to, again, write these coordinates in terms of the average energy per bit. And when I do that, whoops, you can see that this coordinate, a square root of t, in this case would be the square root of 2 times the average energy per bit. So now if I look at these two systems, S1 is longer in the on-off keying than it is here. But that's okay, because when I calculate the average energy per bit, I'm going to get the energy is 2 EB for S1. I'm going to get 0 for S0. When I find the average, I'm going to get rid of that factor of 2. And here, of course, the two energies are the same, and so I'm going to get EB. So clearly, this new second representation is the correct representation. Everything is referenced to the average energy per bit. And we'll see that this is a defining characteristic of signal space. Signal space is, by formulation, where the length is directly proportional to the energy, and the normalization that we choose is where all energies are referenced to the average energy per symbol. For the binary case, the average energy per bit. So now let's look, what can we get from our geometric intuition for this system? So we can see that if we look at the separation between these 2 points which represent the symbols, here's the symbol vector, this point represents where that vector points, and we can see that these two are separated by a distance of 2 times the square root of EB. In the case of on-off keying, the distance between the 2 symbols is the square root of 2 times the square root of EB. And of course, the square root of 2 is 1.414, and therefore 1.414 is smaller than 2, which means that these two are closer than these 2 symbols. And we can sort of, see that by eye. So right off the bat, with this new normalization, I'm starting to suspect that the antipodal will have better performance, because in terms of the same energy per bit, they seem to be farther apart. And intuitively, farther apart should mean fewer errors for the same perturbation of noise. So let's go on now. Before I calculate the performance, though, my first tip-off was this distance, and I have a suspicion. Before I do that, I have to ask myself, what is the map receiver? And in this case, assuming that they have equal priors, it would be to just choose the signal that's closest to the received signal. And to do that, what am I going to do? Well, here we can imagine a threshold being placed at the midpoint of these 2 symbols, because therefore, if I know the midpoint between the 2 symbols, then instead of having to calculate the distance, like here, I could have calculated the distance between the head of this green arrow and the head of this red arrow, and the distance between the head of this green arrow and this blue arrow. And of course, the received signal in this case is closer to the positive or the logical one. But if I don't want to actually calculate distances, what I can do is instead use these thresholds. And I know that the equivalent of saying choose the closest signal is compare the signal to a threshold located at the midpoint. So notice that the threshold falls in different positions in these 2 cases. In this case, it's for antipodal, it's located right on the origin. And in this case, it's at the midpoint, is not at the origin, but rather halfway along the S1. So the map receiver for equal priors, or the equivalent of the maximum likelihood receiver, is if R is positive, if the coordinate of R is positive, choose S1. If it's negative, choose S0. And, in the case of on-off keying, the midpoint falls halfway between. The midpoint is at 1/2 of the square root of 2 square root of EB, which is the equivalent of the square root of EB over the square root of 2. And so in the antipodal case, I'm comparing it to 0. And in the on-off keying case, I'm comparing it to the square root of EB over 2. So in terms of complexity, they're the same complexity. It's comparison with a threshold. The threshold just happens to be different. Now we get on to the interesting part. Now we're going to calculate the bit error rate for each one of these modulations. So intuitively, I think that I'm going to get better performance for antipodal, but I'd like to know how much better. How can I quantify that? So now it's time to calculate the probability of error. So probability of error can be written using the law of total probability as the sum of the probabilities of the 2 types of errors that could occur. For instance, I either send a 0 or I send a 1. Those are the 2 probabilities, 2 possibilities. So if I send a 0, then when will I have an error? I will have an error when I send a 0, but the received signal is positive. It should be negative, but it's positive, and because it's positive, I'm going to choose the wrong one. So this is called one kind of error event. It's the error event in the case that a 0 is sent, but a 1 is chosen. Now the other kind of error it can have is that a 1 is sent, but a 0 is chosen. And the total error is the sum of the total error probability is the sum of the 2 types of error, the probabilities of the 2 types of errors which can occur. So in terms of writing them, you can see we've written them here in terms of the conditional probability density. It's the probability that R is greater than or equal to 0, given that a 0 was sent, and that, of course, is weighted by the probability of 0 was sent. So again, the first type of error, I say 0 is sent, and so the error occurs when I choose 1. And when do I choose 1? It's when R is positive. And the opposite here, I'm sending a 1, and when am I going to choose 0? If I send 1 and I choose 0, that's an arrow, and I choose 0 when R is less than 0. Now I'm going to make the assumption of equal priors. And equal priors means that I can replace the a priori probabilities in this probability of error calculation to be 1/2 equal for the binary case. So with this assumption of equal priors, we can go on with the calculation. And in this case, what happens, what does it mean when I say that a 0 is sent? So the next step is to condition on the data sent. And the data sent here, when I say a 0 is sent, what does that mean? A 0, remember, what are the coordinates of the waveform for a logical 0? The coordinates in the antipodal signaling was a negative square root of the energy of bit, so minus square root of energy of bit. So when is the received signal going to be above 0? It's when what was transmitted minus the square root of EB plus the perturbation of noise, when that is greater than 0. So here I have a chance. I want to see R greater than 0, what that means, and here I can write it in terms of what was sent. So if a 1 was sent, if a 1 was sent, then we know that the R is going to be the square root of EB plus N. Okay, so now I see the conditions. I say conditions was 0 sent, and now I sort of turn that into what does that mean about the received vector? Because I know a 0 is sent, what does that mean about my received vector? Okay, so now I'm going to use this information about what the received vector is to look at this probability that this inequality holds. So what is the probability that R is greater than 0, given that R is equal to minus the square root of EB plus N? That's this first term. Well, I can write this in a much more simple manner by saying that is just the probability that this R, so I can take this in and put it minus the square root of EB over square root of EB plus N, that sum is greater than 0. So this condition makes it easy for me to write this probability. And the same thing happens in the second term. The probability that R is less than 0 is the equivalent of asking, is the square root of EB plus N less than 0? So now that I have these very straightforward inequalities, I can solve for N, and this becomes the probability that N is greater than the square root of EB times 1/2 plus 1/2 that the probability of the probability that N is less than minus the square root of EB. So due to the symmetry of the Gaussian density, and of course when I ask the question, what's the probability that this N is greater than the square root of EB, this probability density I know is Gaussian. And so if I take 1/2, well, let me go to the side here and just recall. This is a 0 mean Gaussian variable, so the mean is here, and I'm asking the question, what is the probability that it's greater than the square root of EB, or that it's less than minus the square root of EB? Now, due to the symmetry, well, first of all, probability that's greater than is the area under the curve here, and because of the symmetry of the Gaussian distribution, these two areas are equal. So if I take half of one plus half of the other, it's like getting one of them. So that's why here I say that this is just equal to the probability that N is greater than EB. And this is easy to calculate because I know this density. So I know that this area under the curve is just the integral from the square root of EB from this point all the way to infinity. So it's the integral of the square root of EB to infinity of the Gaussian distribution. So this calculation comes up all the time in communications and in many different applications that draw on the Gaussian distribution. And because this integral occurs so often, we give it a name. And the name that we give is this Q function, or sometimes called Markham's Q function. So this Q function is 1 over the square root of 2 pi, the integral of x to infinity of e to the minus x squared over 2. So it's not quite what we have here in our probability of error, but it's very close. All we have to do is change the argument of our integration so that we replace n with, just write it here, so we say let u equal n over the square root of 2, and if we make this substitution, then we would get this equivalent integral, and that one looks just like our Q function that we've defined. So using this name for this integral, we can say that the probability of error for antipodal signaling is the Q function of the square root of EB over sigma. And remember, sigma is just the square root of n0 over 2, and so we often want to write it in this form, and that would mean that the probability of error for antipodal signaling is the Q function of the square root of 2 EB over n0. Okay, so you recall that I said that there are 3 topics of greatest concern in communications, and one of them was the bit error rate versus SNR, or power efficiency. And we can see now that we're getting close to being able to answer this question, and that's because here I have a ratio of the energy per bit divided by the noise. So I'm getting something that looks very much like a signal to noise ratio. In fact, it's sort of like a digital version of the signal to noise ratio, and we'll be talking about that more. So using this notation, I can just relate the two, that the probability of error is, in our case, because we're looking now at EB over 2, excuse me, sorry, so sorry. This was for antipodal, and I could do the same thing for the second case of on-off keying. It's very similar, so I'm not going to go through it again. I'll just cut to the chase, and the development is very much the same, except that the threshold is different. And because of the threshold being different, our calculation comes out a little differently. And in fact, when we go through the math and we get to the end, the probability of error for the case of on-off keying is Q of the square root of EB divided by N0. So here's a summary of what we found. And instead of calling it antipodal signaling, now I'm going to give it another name. I'm going to call it binary phase shift keying, since this is the name we typically give to antipodal signaling. They're both, remember, not returned to 0. They're just simple square waves. So on-off keying, S1 of t is a non-return to 0 signal. S0 is just sending nothing. And so if we look in signal space, this would be the signal space representation with these vectors. And we've found the probability of error for this system is the square root of EB over N0. The BPSK system we looked at, of course, set the same symbol waveform for symbol 1. It was NRZ. And the logic 0 waveform was just the negative of the logic 1 waveform. This is the representation in the, doesn't want to stay put, in the signal space, and this is the probability of error. So I just repeated myself, but we can see there's a factor of 2 different here. It's like I have twice as much energy here than I do here, sort of the equivalent. So we can think of it as something like a 3 dB penalty for the performance of on-off keying versus BPSK. So if my communication system is being judged by power efficiency, then I would say that BPSK has got a real edge to the performance. Now, perhaps the complexity of the receiver could be less with on-off keying. For instance, systems with optical communications could have light, no light, and perhaps the component for generating light, no light could be very, very inexpensive. And so although the power efficiency might be lower for on-off keying, perhaps there are other reasons why this might be a good choice. So it's good to have a lot of choices for modulation so that we can make a trade-off on the different factors that are important in a communications system. So now I'd like to plot this probability of error versus the signal-to-noise ratio. And I don't want to get into the exact form now. We'll be talking about that a lot more in the coming weeks. But for now, I'd just like to draw your attention to the general form of these curves. Okay, so the x-axis is some signal-to-noise ratio. The y-axis is the bit error rate. I use a logarithmic scale for the bit error rate, very, very common. And the signal-to-noise ratio is typically written in dB. So although it doesn't appear to be so, this is also logarithmic scale. We see here the typical form of a communications bit error rate curve, which we call a waterfall. So it starts up so that when the signal is very, very weak, when the signal is so weak that I'm making half the, it's almost just noise, then half the time I would get the wrong bit. And my probability of error would start at something like a half. And then as my signal gets stronger and stronger and stronger, the probability of error goes down. So we start off with terrible probability of error when the signal is very weak, and as the signal gets stronger, as the signal-to-noise ratio gets higher, we start falling, and that's why we call this, a waterfall curve. Now, you'll notice that this waterfall, there are two waterfall curves here, one for BPSK and one for on-off keying. And if I were to look at the distance between these two curves, we would see that the distance, I guess we can look down here at the x-axis, is about 3 dB, which makes perfect sense because I have this factor of 2 in the probability of error calculation. So if, for instance, I wanted to achieve 10 to the minus 5 bit error rate, I would need something like 9 dB signal-to-noise ratio for BPSK, and I would need something more like 12 dB signal-to-noise ratio for on-off key. So there's a 3 dB penalty from using one to the other. So in general, when we look to read a bit error rate curve, you'll be looking at that, the distance between curves, and remember that the origin is better. So anything closer to the origin is going to be a better or more power efficient modulation. Finally, I'd just like to mention that this Q function is similar but not exactly the same as what is called the error function in MATLAB. So do be careful because sometimes you'll be using MATLAB to calculate bit error rates, and the relationship between this Q function and the ERF function in MATLAB is quite simple and given by this expression. I also have here a very simple approximation, or upper bound, but a good approximation for the Q function. For x greater than 3, you will get something, and this is for bit error rate, excuse me, for signal-to-noise ratios. Bit greater than 3 is very likely. A good approximation to this is just an exponential. So if you just had a calculator, you could do it with this. Okay, so that is our first foray into calculating bit error rate. Our first time we saw a bit error rate curve, a very important concept, but here we had it for a simple binary case, but we'd like to expand it. So we'd like to take our intuition we learned here and apply it as we go into multidimensional space. Before I do that, we're going to talk about a couple more practical issues in terms of pulse shaping, and that will lead to the first homework assignment.